Welcome to Frontiers of Research. I'm Antoni, and today we're exploring one of mathematics' most captivating stories, the Poincare Conjecture. We're joined by Dr. Rachel, our topology expert, and Josh, who will help us navigate this fascinating mathematical landscape. This conjecture, first proposed by Henri Poincare in 1904, stood as one of mathematics' most challenging problems for nearly a century before its dramatic resolution by Grigori Perelman in 2002. It's a story that touches on the very nature of space itself and showcases both the depth of mathematical thinking and the sometimes surprising paths to mathematical truth.
Henri Poincare was truly a mathematical giant of his time. In the late 19th century, he essentially created the field of topology, the study of properties that remain unchanged when shapes are continuously deformed. His work on what we now call manifolds was revolutionary. The conjecture arose from his study of three-dimensional manifolds, particularly what we call the three-sphere. What's fascinating is that Poincare actually first proposed a false conjecture, found a counterexample himself, and then refined it into what we now know as the Poincare conjecture. This kind of intellectual honesty and willingness to publicly correct oneself was characteristic of Poincare's approach to mathematics.
Could you break down what exactly the Poincare conjecture states? I know it has something to do with spheres, but what makes it so fundamentally important in mathematics?
The conjecture, at its heart, is about recognizing when a three-dimensional shape is essentially a sphere. More precisely, it states that every simply connected, closed three-manifold is homeomorphic to the three-sphere. In simpler terms, if you have a three-dimensional space where any loop can be continuously contracted to a point, and there are no holes or boundaries, then that space must be topologically equivalent to a three-dimensional sphere. What made this conjecture so profound was that while we could easily verify this for two-dimensional surfaces, the three-dimensional case proved far more challenging. The conjecture also suggested a deep connection between local properties, the ability to contract loops, and global properties, the overall shape being spherical.
The history of attempts to solve the Poincare conjecture is fascinating. Rachel, could you walk us through some of the major developments and attempts over the decades?
The first major progress came in the 1960s with Stephen Smale's proof of the generalized Poincare conjecture in dimensions 5 and higher. This was followed by Michael Friedman's proof for dimension 4 in 1982, which earned him the Fields Medal. But the original three-dimensional case remained stubbornly resistant. Mathematicians developed powerful new tools: geometric flows, minimal surfaces, and various surgeries. But complete success remained elusive. Wolfgang Haken and Christopher Zeeman made important contributions, and William Thurston's geometrization conjecture in the 1970s provided a broader context that suggested a possible route to the solution.
Could you elaborate on Thurston's contribution? How did his geometrization conjecture relate to the Poincare conjecture?
Thurston's geometrization conjecture was a grand vision that included the Poincare conjecture as a special case. He proposed that all three-dimensional manifolds can be decomposed into geometric pieces, each with one of 8 possible geometric structures. This was encircled by the uniformization theorem in 2 dimensions, but was far more complex. The Poincare conjecture would follow if you could prove geometrization for simply connected manifolds. This reformulation was crucial because it suggested using geometric flows, ways of deforming the metric of a manifold, as a possible approach to the proof.
This brings us to Richard Hamilton's groundbreaking work on the Ricci flow in the 1980s. Rachel, could you explain how this set the stage for Perelman's eventual solution?
Hamilton's introduction of the Ricci flow was revolutionary. This geometric flow, similar to how heat spreads through a material, smooths out irregularities in the geometry of a manifold. Hamilton showed that under Ricci flow, manifolds tend to become more regular and uniform. He proved several crucial results and developed many of the technical tools that would later be essential. However, he encountered serious difficulties with the formation of singularities. points where the flow breaks down. These singularities were one of the major obstacles that prevented a complete proof.
And this is where Perlman comes in. How did he manage to overcome these obstacles that had stumped everyone else?
Perelman's breakthrough came through a deep understanding of these singularities. He developed new techniques for analyzing them, including what he called surgery on the Ricci flow. When singularities form, his method essentially cuts them out and continues the flow. He also introduced the crucial concept of entropy for the Ricci flow and showed how to control the topology through these surgeries. What's remarkable about his proof is that it's not just a solution to the Poincare conjecture. Si pravers irsocrois, that erzitari harchiars. Thurston's entire geometrization conjecture, his 3 papers posted on R-Carve between 2002 and 2003, were revolutionary not just in their results but in their techniques.
The verification of Perelman's proof was itself a fascinating process. Could you tell us about how the mathematical community responded and verified this momentous achievement?
The verification process was intense. Several teams of mathematicians worked to understand and verify Perelman's arguments. Notably, Huaidong Cao and Xiping Zhu published a complete exposition, as did John Morgan and Gang Tian. Bruce Kleiner and John Lott maintained an online commentary explaining the proof. What's particularly interesting is that Perelman's original papers were quite sketchy by mathematical standards. He provided the crucial ideas and left many details to be filled in by the community. This led to some controversy, but ultimately his insights were validated, and he was awarded the Fields Medal in 2006, which he famously declined.
Beyond solving this specific conjecture, how has this work influenced mathematics more broadly? What new doors has it opened?
The impact has been profound. The techniques developed for this proof have found applications in many areas of mathematics and even theoretical physics. The study of geometric flows has exploded, with applications to problems in differential geometry, mathematical physics, and even applied mathematics. The methods of dealing with singularities have influenced other areas of partial differential equations. Perhaps most importantly, it demonstrated the power of combining geometric, analytic, and topological methods in new ways. The proof has also sparked interest in understanding similar questions in other dimensions and for other geometric structures.
Thank you, Rachel and Josh, for helping us explore this remarkable mathematical achievement. The story of the Poincare conjecture, from its formulation to its solution, exemplifies the deep beauty and challenge of mathematical research. For our listeners interested in learning more, we've included references to key papers and expositions in our show notes, including Perelman's original archive posts and the subsequent detailed expositions. Join us next time for more explorations at the frontiers of mathematical discovery.